Hello, everyone. Come on in. Sorry for the delay. I don't know what took it so long, but here we are. Got 9 of you here. Anybody have any questions while we're waiting for some more people to show up?
Yes,
When is the? I'm sorry, Tristan. You can go ahead.
that's fine. You go first.
I was just gonna say, when are the chapter 15 homeworks due? Because I know it says on the online it says the 29th, but I was just wanting to double check.
The 29th, that would be what? Let me check what day that is.
Monday.
Monday. Yeah, that sounds about right. That gives you, because we actually more or less finished chapter 15 last time, but I'm actually going to revisit it today to give you some more examples. So I think Monday after Thanksgiving should be fine for that one. Is that the last of the homeworks, or is that the concepts, or is that
That's the whole thing.
the whole thing?
Yeah,
Okay,
it's all the last of the homeworks.
I'll move it to Wednesday just to be nice. I'll give you a little bit more time in case y'all are doing something fun over Thanksgiving break. All I gotta do is remember to do it. If I don't remember to do it, send me an email, because I'm a goober and don't remember things. I'm old. I'm so old. I'm like Dr. Nefario.
So we should have a chapter 15, or like that's the last homework that we can start working on. So we haven't covered anything after that, or?
Yeah, we haven't covered anything after that. I was going to start in today on elementary particles, but I think instead, I decided instead to show you some more problems that are like wave motion problems. So I'm going to work those today instead.
Works with me.
Yes.
Okay.
David,
I got a quick.
Christian, go ahead, Christian.
So I have your lab on Thursday.
Mhm.
Will there be class on Thursday?
No,
Okay.
nobody has any classes Wednesday, Thursday, Friday, Saturday, or Sunday.
Okay. Do you still want the lab turned in though by that deadline?
Nope. In fact, Friday, I thought I took and changed the due dates on all those labs to the lab day after Thanksgiving. If it's not, still ignore it, because it's definitely supposed to not be due until the lab day after Thanksgiving.
Okay, I understand. Thank you.
Okay, no problem. And this video will be up later too, so make sure you can come back and check that if you get nervous and say, I'm not sure, I don't have to turn it in. So I'm telling you, you don't have to turn it in. I think I might have even made it at the other lab. I know I did it for one section. I made last week's lab as well as the week before's lab, both due after Thanksgiving. So if you were that group, then maybe you got that too. I know it was the Springs lab some students had problems with. So anybody else have anything?
I do one question on the lab,
Go
but
for
I
it.
think I'll wait till after class.
Okay, no problem. That won't be a problem. All right. Well, what we're going to do is I've got some problems that are like some of the problems at the end of the chapter, and I want to work those out for you so you can have some understanding of how they're done. Now, this is horribly written. I've basically tried to make similar problems to problems in the end of the chapter, but I didn't want to violate copyright, so I changed things about them quite a bit, but I still wanted you to see, and I definitely don't want to, one, violate copyright, but two, I don't want to take a problem that an instructor might assign because it's even and it's in the back of the book, and therefore they could assign it as a homework that they could grade for correctness. I don't want to take one of those even number problems and solve it. So I had to change it up enough so that wouldn't be the case. So that's what I've done here, but I wrote it on what do you call it, notebook or notepad or whatever that crappy app is. So like if I tried to change the Greek letter or the M to the Greek letter mu, it changed all the letters to Greek. So it's just crappy script. So just bear with the screen share that I'm getting ready to do. That's not it. That's it. Okay. So this first question, it says a transverse traveling wave is given by d equals 0.500 times the sine of 8.50x plus 44.0 t, where d and x are measured in meters and t is in seconds. What I want to know is what is the wavelength the frequency, the velocity, both magnitude and direction, the amplitude, and the maximum speed specifically of any point on the string. Okay, so that's really what I'm shooting for here. I'm going to go ahead and I'm getting ready to show you. Today is 11/23/21, and this is PHY 241 D01C, and this is example 1. So what I have is D is equal to 0.500 sine of 8.50x plus 44.0 t. Okay, and what they want to know is they would like to know the wavelength lambda, the frequency f, the velocity, which I'll indicate magnitude and direction by writing it as a vector velocity, the amplitude, which I called A like we do normally, and V max and V min. All right, now I'm going to share my paper screen, or share my document cam, in other words. Stop sharing it. Hopefully everybody's gotten all the information they need off of that. Now I'm going to switch to my document cam. And you see what I've written down, hopefully, once that ever comes up. You see that I've written down the function. And I've managed to write down the variables that I'm solving for. So that all should be known, and we can start working on it now. Sorry, I was doing some multitasking. Zoom is telling me it's converting a meeting, and I'm trying to put it in the right folder and all that while teaching you. So the general rule was, and I dumbly called the function for that's an answer to the wave equation. I dumbly called it x is equal to, which is really stupid because it's got an x in it. You can't really have that. So just keep that in mind. That was stupid. What I'm going to do is translate that to let you see it. So what we had was the second derivative of d with respect to x squared is equal to 1 over v squared times the second derivative of d, the amplitude, with respect to t squared. So you can see, in fact, this is the wave equation. And what I say is a solution should be d equals a cosine omega t, or excuse me, sorry, I slipped into harmonic oscillator mode. Kx minus omega t plus phi. So that whole thing inside of the cosine function, that's called the phase. The kx minus omega t plus phi, that's all called the phase. And really for the cosine function, you can think of it as that part of the wave from here to here. Okay, because k at x equals 0 is exactly that point. At x equals 2 pi, it's that point right there. Okay, well, sort of equivalent to 2 pi. So it's actually like when x is equal to lambda over 2 pi, something like that. All right, so what we're going to do is we're going to compare these two, and I want you to do this type of problem specifically for a couple different reasons. One, I want you to see that it doesn't matter that I happen to choose cosine. You can choose sine. You know, for instance, sine looks like this, and cosine looks like this, which I'll carry some of the negative with it. Cosine's just this from here to here, right? But you can see it looks just like sine if I started early. So you can see that cosine and sine are just related by one of these phi shifts. So if I put a phi in there, I could make this cosine. Or if I put a specific phi in cosine, I could make it a sine. So I want you to realize that that's perfectly acceptable for someone to call it a sine, and it's not contradicting this. And since the sine and cosine both wobble back and forth between +1 and -1, whatever you put in front of them is just going to multiply that 1 by that amount. So that really is just the amplitude of the wave. So that's part of what you need to see. Also, part of what you need to see is that this kx minus omega t is a real thing. We've defined what k is, and that's pretty hard. Students sometimes don't really get the K, but it technically is something that we use as a vector quantity. And I'll explain that when I'm talking about the magnitude and direction of the velocity, but it's normally expressed as a vector. In our case, it's not. But let me give you a nice parallel to it. I did it before in class, but I think maybe a second time might be in order. What we knew specifically was omega from the angular motion stuff was equal to 2 pi times the frequency. But we also knew that the frequency was 1 over the period. So guess what? You've got omega, which does appear in the solution for a wave equation. That omega appears, and in fact, that omega is 2 pi over t. Now, if you make a plot of d versus t, where this is t, that basically is the distance along the time axis that you have to go before the wave starts repeating itself, right? Now I've introduced another quantity, k, which is 2 pi over lambda. But notice if I make a plot of d versus x, that lambda is the minimum distance you must go for it to repeat itself. So you can see lambda and t are very, very similar things. So k is just like omega. It's just what the wave motion does in space versus what the wave motion does in time. Now that we got that and you have some understanding, hopefully that'll help you remember what k is. And then they'll normally say k, they'll call it a vector quantity by putting a vector symbol over it and putting a unit vector that points in the direction that the wave is propagating. So in our case, our wave is propagating in the x direction. I'd write I write this and put an I hat next to it. That would be making it into the wave that into the vector that it is.
What
Now,
is lambda again?
Lambda is the wave.
What is it representing?
Yeah, lambda is the
Okay.
wave. Okay. So what the other part I want, or one of the other parts I wanted to show you is that, yeah, these things still, even though I switched from cosine to the sine, they still mean the same thing. So this A is still that A, this K is whatever is multiplied by X, and this omega is whatever is multiplied by T. And if I have something added to it, that's got to be the phi. If it's subtracted from it, that's the negative of phi. So now I can immediately start answering questions. For instance, I can answer the lambda question. And of course, since K is equal to 2 pi over lambda, then lambda must be equal to 2 pi over K, which is 2 pi over 8.50. Now, if you look at this, the sine, you sort of assume it's always going to be taking a sine of a radian. So this is a meter, so this must be radians per meter. And that's exactly what we're going to do, is we're going to say the units here are radians per meter. And in some sense, you can think the 2 pi is converting radians into cycles if you want to. But now when I do this math, I get that the wavelength is I just divide 2 pi by 8.50. I get 0.73920. I carry 2 extra sig figs there. And you see that's has units of M now, because radians in the bottom with meters in the bottom of the bottom becomes meters per radian there, and that 2 pi radians cancels out.
Can I ask a question?
Yes.
So are W and K always going to be the same because they always fall in the same place on the x-axis?
Well,
Because it
it's
looks
not
like
right
it's
to
one
say that they fall in
period.
the same place, but yeah, it's that's the deeper thing I'm trying to get you to. Is
All right.
absolutely they're the same thing, and they're always going to be that 2 pi over T and that 2 pi over lambda.
All right, got it. Thank you.
No problem. Yeah, that's a big thing to understand. And parts of this I didn't get that well the first time I took the course, so I'm trying to be really pedantic and show you all the parallels and stuff so that it helps you. So that's the wavelength, and that literally means if we plot this wave, which actually this wave happens to be a sine wave, so I'd have to do that, and that's my D equals blah, blah, blah. So that lambda is basically where that part of the wave hits there. Now we got another function, another question, and that's what is the frequency? Well, the frequency, to get that, we know that omega is equal to 2 pi times f. So the frequency must be omega over 2 pi. Watch out on this. I always just randomly will multiply by 2 pi instead of dividing by 2 pi. So keep me honest on this. But I can see on here, of course, the omega has to be the thing in front of the t. So I'm going to say it's just 44.0 over 2 pi. Again, I need to think about the units though. Obviously, this times t must give out radians. So this must be radians per second. And that's exactly what we expect omega to come out to be. So that's radians per second. And you're going to get 2 pi converting the radians into cycles. Now, you don't always have to think about erasing the radians or adding radians, but sometimes you sort of need to, because like frequency really means the number of wavelengths that pass you by in a single second. So you really need it to be like wavelengths or cycles. And that 2 pi is the number of radians in one cycle. So you can think of this as radians per cycle. You can always think of 2 pi . Okay, so just keep that in mind. Now, when I actually do this 44.0 divided by 2 pi, I end up getting something pretty large. It's 7.0028, giving 2 extra sig figs. And you see that this becomes cycles per second, which is hertz. That's actually my frequency. And I will box that off so everybody can see it with bright, pretty colors. Look at the pretty colors. Any questions
44
on
over
that?
2 pi.
Yes, it should be 44 over 2 pi. From omega equals 2 pi f, f would be omega over 2 pi. Now, we know the kindergarten version of the wave equation. I told you before that the velocity, which is what they're asking for here, magnitude and direction, the velocity we know is frequency times wavelength. And I just calculated the frequency and the wavelength. But guess what? If I'm actually taking a test and I was asked to calculate a frequency and I was asked to calculate a wavelength, then I was asked to multiply frequency times the wavelength, I would look for some other way of doing it, because what if I made a boo-boo getting this one, or I made a boo-boo getting this one, then my new third answer is going to be completely wrong, and the instructor might not see what I did wrong and therefore not give me any credit. So it's best not to use the actual calculated values. It's better to use from the values they gave you initially. So here's a neat way where I can interpret this without using f times lambda. So for instance, I can realize that f is actually equal to, if you think about it in terms of omega and all that good stuff, you can see f is equal to omega over 2 pi. So I'll say omega over 2 pi. And then I can say, wait a second, I solved for lambda earlier and that was 2 pi over k. And you see the 2 pi's cancel out and I just get omega over k. And those are quantities that were given to me. So it's better to use those than to use the calculated ones. And this is in fact the wave velocity. In fact, W over K is what appears in this slot right here when you plug this into the differential equation. I say W, it's omega over K is what appears in here. In other words, you'll get K squared over omega squared in front of the d2d over dt squared. So with that in mind, I'm going to take the omega, which was 44.0 radians per second, and I'm going to divide it by the K, which was 8.50, and that's actually thought of as, you could think of it as radians, because it's 2 pi over meters. So that 2 pi and that could actually be just radians, because it does convert, for instance, the this quantity times meters gives you radians. So you can do that. You see the radians cancel out and I end up getting meters per second. So when I divide 44 by 8.50, I get 5.1765 meters per second. And that's equal to the velocity. But it doesn't necessarily give me anything about magnitude and direction. Okay. So let me explain the magnitude and direction. First off, in general, the velocity for a wave equation is d is equal to a cosine k dot r minus omega t plus phi. Okay. In other words, if when you treat k as a vector that points in the direction of travel, like I did there, you know, this case, it happened to be traveling in the x direction. And if you realize that r is just the vector x I hat plus y j hat plus z k hat, you'd see, oh, okay, so this is just a kx is just a special case of k dot r. So what this is telling you, since our function had k times x in it, this means it's going in the positive or negative x direction. So 8.50x implies v is in the plus or minus x direction. So that's what I mean by magnitude and direction. Now I got to figure out whether it's positive or negative. And this is what I do. Remember, I told you earlier that this thing right here, you can think of as, for instance, it's a sine wave. It's just this chunk right here. That's the phase of it. And in reality, really, you're saying a particular point on there. You might decide to say that point, or you might decide to say that point, or you might decide to say that point, or that point, or any point on there. But really, you're looking at one point on there and all the stuff with it and just imagining that moving through space. That's what the wave is doing. So if I do that, if I want to think about how that moves, then what I do is I take this phase and I set the phase equal to a constant. Set phase equal to a constant. Okay. Now remember, the phase is what you take the sine or the cosine of. So it's reasonable to think in terms of radians. So I'm going to choose that particular point by setting the phase equal to 2 pi. Okay. So I'm going to say 2 pi is equal to 8.50. We've already discussed this. This 8.50 is radians per meter times x plus 44.0 radians per second times t. So this explicitly, by putting it equal to 2 pi, explicitly makes me consider what that point right there is doing. Everybody see that point? It's the end of the 2 pi cycle of sine, because I had a sine function. So if I solve this for x, what I get is x, and that's literally the coordinate of that dot on the wave. So the coordinate of that dot as a function of time, I can write x of t is actually equal to 2 pi radians over 8.50 radians per meter. So I pulled that over here. That became, I'm going to pull this over here, and that's going to become negative. So I'll say minus 44.0 radians per second over 8.50 radians per meter times t. Now, this quantity happens to be just the wavelength. So I say x of t is actually equal to the wavelength minus, and 44 over 8.50 is in fact the wave velocity. So that's v times t. And that's exactly what we expect it to be, right?
Oh, that's really cool.
Yes. So at t equals 0, this just becomes wavelength, which is exactly what that dot is. And now you can see, oh, it starts off at there, but look, as t gets larger and larger, it's going that way. So in fact, velocity is equal to 5.1765 meters per second negative I hat. Basically, I just put it back in vector form so it's easy to specify the exact direction and magnitude. And the negative, of course, is saying it's moving in the negative direction, and the I hat saying it's moving in the negative x direction. So that's why when you have x minus kx minus omega t, that's moving in the positive direction. And when you have kx plus omega t, it's moving in the minus direction. Okay, I did not get this when I took this course. In fact, I put this sort of play together, I think somewhere in the third semester of the course, and then I started to understand it. But I want you guys to be better than me. I want someone to point that out to you, and that's why I did that. Okay, so you see the actual position as a function of time of that little dot on the wave at t equals 0. It's exactly x equals lambda distance, right? And then it moves to the left with a velocity of 5.17 or 18 meters per second to the left. So you can see over time, it's going to go like this. Ain't that cool? So hopefully you guys will be better than me by figuring this out earlier, or at least having been shown it, and you can mull it over in your brain and eventually it'll sink in a little better. So we've now gotten the velocity. All we have left is the amplitude and the V max and min of a spot on the wave. So the amplitude, remember, was just the thing multiplied by the trig function. So in this case, we can see our amplitude is just 0.5. And since it has to come out in meters, we'd say A is equal to 0.500 meters. And that's exactly right. Now, the V max and V min, what we want to know is the maximum velocity that any point on the string is going to get. This is a wave on a string, say. So the maximum velocity is going to get. Now, we have the displacement d as a function of time, and it actually is going to point sort of like perpendicular to the x-axis. So we can sort of think of d as the y-axis if you wanted to. And what's going to happen is as the string goes by, you know, this string particle right here was at 0, but at one point it's going to go through this hump. Or you can think this particle right here is initially here, but remember this wave is moving this way. So as it moves, it's going to go higher, 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 and then it's going to go lower, 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 and then it's going to go higher, higher, higher. And what you want to know is what's the fastest that dot ever moved up or down. We'll call the fastest it moved up the max velocity, and the fastest it moved down the minimum velocity.
I
But
thought it was going at a constant speed.
yes, the wave itself, which is moving this way, is going at a constant speed. But this spot on the actual rope or string goes various speeds. In fact, it has a 0 speed right there and right there. It has a maximum in the negative direction speed there. It has a maximum in the positive direction speed there and there. So yeah, there's two types of motion going on here. And if you don't separate those, it starts to get a little confusing. So remember, the wave is just moving this way, and the rope particles aren't moving left and right at all. That would require some of the longitudinal part like an ocean wave does. But the waves on the string, they're just going, you know, when this part right here gets next to a part of the rope right here, it pulls it up. So it becomes this part next. And then this part pulls that down. So it becomes this part next, and so on and so forth. So the wave actually looks something like this. That's initial. And then like that. So slowly but surely, these little pieces of rope, which were initially just that, are going through these cycles. Okay. So can anybody tell me how to get, since the displacement is the direction it's moving in the y direction, say, anybody tell me how that you know, distance per time or y per time can become a velocity, what do you have to do to it in terms of velocity and time?
You have to take the
The
derivative.
derivative.
Excellent. Y'all got that a lot quicker than my other classes did. Excellent. So yes, V is equal to dd over dt. Again, that could have been y or anything, so don't worry too much about it being a different symbol. But when we do that, we can see, okay, well, the function, remember, d, I'll write it again here, d is equal to 0.500 meters. Notice I'm putting the units in now, times the sine of 8.50 radians per meter times x plus 44.0 radians per second t. Sorry, I ran out of space. Okay, that's the actual function. So I'm going to take the derivative of that, and obviously I'm going to get 0.500 meters. I'll leave a space. The derivative of sine is actually equal to cosine. And then, of course, I took the derivative of the cosine with respect to the phase. Now I got to take the derivative of the phase with respect to t. So this one's 8.50 radians per meter times x plus 44.0 radians per second times t. Now I got to take the derivative of this with respect to t, and I'll get 44.0 radians per second. So just like the amplitude tells how high and low the sine wave gets, that value and that value, well, this amplitude looking thing gives me the max and min speed. So V max is positive 0.500 meters times 44.0 radians per second, which equals 22.0 meters per second in the positive direction. And V min, of course, would be negative 22.0 meters per second. And notice they are actually in the positive d direction. And this one's in the negative d direction. Of course, you know, I don't like that, saying one's velocity min and the other one's velocity max. Min and max is something I think about the actual magnitude of the thing. Those two guys have the same magnitude, and I would call them the maximum speeds, period. The fact that it's negative is just saying it's going in the opposite direction. But as far as I can tell, this, when your book asks something like this is what I think they mean. Obviously, the slowest speed the particle is going to have is when it reaches the crest or the trough, at which time it'll have a velocity of 0. So it may, when your book asks for this kind of thing, it may actually be wanting V min equal to 0. But I'll just give it with that caveat because I'm not really sure what they're talking about. I suspect it's this. Okay. So that's a very typical problem, and it's what I want you to do, because remember, just like we did with chapter 14, we solved the simple harmonic oscillator, and in solving simple harmonic oscillator, you weren't necessarily supposed to learn how to solve a differential equation, even though I hopefully showed you how in that particular case. Really what you were supposed to do is use that idea to say, hey, whenever I have an equation of this form where a times d2x over dt squared plus b times x is equal to 0, or when a times d2x over dt squared plus b times dx over dt plus c times x is equal to 0, those are harmonic oscillator problems, and I immediately know the solution. Okay, and all I have to do is have the initial conditions, and I can figure out what the values of, in this case, it'd be omega, which comes from the b over a, and then you have to know the phi and the a, and those are the two things that you get from the initial conditions. So I'm doing something similar to that with the wave equation. I don't really expect you to know how to solve this. We've told you pretty much this is it. And that's the answer. You just have to now know how to apply this, or how to recognize when someone has applied it and made certain tweakings. So this might have originally been D equals 0.500 cosine 8.50x plus 44.0t minus pi over 2. But the sine of something minus pi over 2 is the same thing, or excuse me, the cosine of something minus pi over 2 is the same thing as sine of that thing without the minus pi over 2. Okay. Any questions on that? All right, so I have another example I want to show you guys. This one's going to take more paper than writing at the bottom. I wrote it at the bottom in a previous class, and it didn't look too good to me. So I'm going to go ahead and say, suck it up. Let's kill some rainforest trees right now, man. I'm going to throw all my straws in the ocean, kill all the little turtles. No, I'm just playing. I tell that to my daughter all the time. She's like reusing straws and other stuff. I'm like, well, how are the sea turtles and dolphins going to die if we don't do this? Of course, I'm joking, but it aggravates the crap out of her. All right, here we go. Example 2. So example 2, I'm going to share screen and show you my awesome notepad document, or yeah, notepad, that's what it's called. So what is the frequency F of a standing wave? So I want to know F is equal to question mark. It's a standing wave. Okay, of a standing wave on a string. If the string has n antinodes, so I'm gonna write that down. It has a length L. It has a mass per unit length, the Greek letter mu. So mu is equal to mass per unit length. And it has a tension, F sub t equal to the tension. So this is really like a derivation question. In fact, your book had something like it, but it actually asked you to prove that F is equal to blah, blah, blah. But I wanted to do sort of like a derivation. Again, I'm trying to avoid violating copyright and stuff like that. And actually, I changed all the wording and all that good stuff. So in this case, what we want to do is we want to imagine a standing wave. Now, the big deal about this is a standing wave really is a wave that's moving left to right, say. So let me turn on my face cam, or let me just turn off everything because I'm crazy. Okay. So if you were to take a rope, like a jump rope or a spring, a long spring, and you go like this with it, what you'd see is as you pull up, you're making that string or that spring lift up with you. And then as you pull down, you make it lower. But what's going to happen is that part that you made go up now travels on, and then that part that you made went down, that travels on, and then the part that you made up, that travels on. Now, that's what's going on, is you're sending these sine waves to the wall or to the other person holding the end of the string or whatever it is. Now, when it gets to the other end, that wall or that person holding it still is going to be pulled upward by the upward hump of the string or the spring, and the wall or the person will respond according to Newton's third law by putting the exact opposite force on it, which means it's going to turn that wave upside down. So it's going to take that positive hump and turn it into a negative hump. Well, that negative hump happens to be running into, just at the same time, a negative hump of the other way of the wave coming in. So what you've got is waves going forward and backwards. The forward ones are upright, meaning the first up is, or the first hump is positive and the second hump is negative, and they're going this way, while the other waves that are reflected are the first hump is negative and the second hump is positive, going this way. If you get it such that you're sending in at just the right rate, then what you'll get is each point in space having a hump and a trough, a crest and a trough right over top of each other every, quarter period. So when it does that, those two add to give you destructive interference and gives you a flat line. So what you end up seeing, say, is a flat line, and then you see a wave like this, and then you see a wave like that. That's how you sort of harmonize it to get what we call the standing wave, because then it doesn't look like a wave's moving at all. It just looks like the parts are going up and down, up and down, up and down, up and down. So you can do it several ways. I'm going to show you maybe the first 3 or 4 and go from there. So let's try, I'm going to call this the solution. So let me show you on my document cam what I'm talking about with all that wording. So this is the solution, and here's my document cam. Dang it, always does it. I hit the arrow, but if I don't hit exactly on the arrow, it gives me something else. Okay, so first off, you don't know anything about antinodes yet. I mean, I've told you what they are, but you probably are not that savvy with them yet. So this is the length of the string that we're talking about. Okay, now the bare minimum is I send a wave, and just as the front end gets here, the back end is there. Now that's going to reflect and come back here like this. What we have here is one antinode. This is the antinode. Nodes are the things that sit still. So that's a node, and that's a node. This antinode is the part that vibrates the most, and this implies n equals 1. But from that, we can see by comparing it to, for instance, the sine wave, that the length is in fact equal to half a wavelength. You see, that matches just this part. Now, if you increase the frequency a little bit and establish another standing wave pattern, this one, by the way, is called the fundamental frequency. And most people also call it the first harmonic. Because these notes, if this was a string of a guitar, for instance, these notes would harmonize. Now, the next case is where I get basically this half going up at just the right time for this half to go down. And then when this half going up gets here, it starts to be reversed, and you get that. So this is n equals 2. In other words, the number of antinodes is 2, and we get that L is actually a whole wavelength. So we say L is equal to lambda. And this is called the second harmonic. But it's also called the first overtone. Okay. Now you do it again. Again, the same length of string L, but this time we're going to get an antinode, and a third antinode. And just as this one gets here, it'll be reversed, and you'll get, that was a bikini top. This is a Martian's bikini top. In this case, you get L is equal to, notice this is a whole wavelength, this is a half, so we'd say this is 3 halves the wavelength. This is n equals 3. Now, if you start to look at that, you realize, wait a second, if I wrote this as L is equal to n lambda over 2, then this part would be 2 lambda over 2, and that's what I got, just plain lambda. And this part would be 1 lambda over 2, which is exactly what I got. And in fact, let's try 4. So what I'm going to do here is cut this in half, cut this in half, cut this in half, and now I can draw it properly. And I'll say this, 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 this. So this is 4 antinodes. So if this hypothesis is right, I'd expect it to be L is equal to 4 lambda over 2, which that's exactly 2 lambda. So yes, that works. So that's our pattern. Our pattern is L is equal to n lambda over 2. Since L is equal to n lambda over 2, you can now say that lambda must be equal to 2L over n. But we want the frequency. Well, we know the velocity of the wave is the square root of the tension divided by the mass per unit length, right? And we also know the velocity is equal to the frequency times the wavelength. So let's combine all that. And I want to say the square root of the tension over the mass per unit length is equal to the frequency times 2L over n. So I think I know what the F is now, and this is what we're looking for. So the F must in fact be equal to n over 2L times the square root of the tension divided by mu. That's it. That's the derivation we wanted. That's the actual expression. Like I said, if you look in the back of your book, there's a problem sort of like this where they're asking you to prove this. So I'll just put here QED, which I like to refer to it as quite easily done. Any questions on that one? Okay, I've got a third problem written up as well. And I'm going to go ahead and show you that and work that up since y'all seem to not have any questions on this. Is this accurate? No questions?
I think it's good.
Okay. Yeah, this stuff's pretty straightforward. I mean, it's got some little tricks to play that when you're trying to derive stuff, but it should be pretty straightforward. So let's move on to the next problem. So now we say a string is connected to a F equals 120 Hertz oscillator. Okay, what an oscillator is, by the way, it's basically a speaker. If you ever looked inside of your car speaker, you'll notice there's a little diaphragm. It's almost made of like cardboard, and it's got like some carpet on top of it or something, and it's got little circular ridges all around it. And at the bottom of it, it's either a chunk of metal or another battery, another magnet. But then below that, inside the speaker, is a big magnet. And that magnet or the magnet on the back of the diaphragm, one of the two, are connected to the speaker wire. And the speaker wire, of course, makes the magnet get stronger and then weaker and stronger and then weaker. So that actually causes the diaphragm to vibrate up and down. And whenever you vibrate air up and down, you're actually making rarefactions and compactions. So you're actually making sound. So if you did that same sort of thing, but instead of connected to music, you just connected to something that went through 120 cycles every second, then that thing would just consistently go up, down, up, down, up, down, up, down, up, down 120 times per second. And if you connected something to the center of that diaphragm and tied a string to it, then you have a nice little oscillator that can make a string of a given frequency vibrate. Okay. So that's what we're looking at here. A string is connected to a 120 Hertz oscillator. The string is run horizontally over a pulley to a mass lowercase m hanging from it. If the mass per unit length of the string is mu equals 9 times 10 to the -4th power kilograms per meter, and the length between the node near the oscillator and the node at the top of the pulley is L equals 3 meters, what is the required mass for antinodes numbering 1, 2, 5, and n? So this is going to be example 3. I'm going to write down the information we need. We need F equals 120 Hertz. We need mu is equal to 9.00 times 10 to the negative fourth kilograms per meter. Your book actually called this quantity in some parts, some of the problems and some of the lines of text, they called this the linear density. So be advised, that's another word for it. I'm going to show you the paper in a second. I just got to write it down first. The L is going to be equal to 3.00 meters. And we want N equals 1, 2, 5, and ... N. Okay. And what we want to know is what is the mass. All right, now I'm able to have copied that all down. Now I'm going to show you the document. Cam. Maybe. I swear every time I hit stop sharing, I've got to hit it twice. Okay. So there's the information we have. What we have here, remember, is that diaphragm of your speaker is almost like a paper plate, and you could use a paper plate if it was a little more flexible, but it's got like little groove parts in it that are sort of shaped wave like this. But now with this one, you took and put a little post on top of it that is connected to it. And of course, there's a battery down here, I mean, a magnet down here and a big magnet down here as well. So that's attracting it back and forth at 120 Hertz. And that's tied to a string. And that string goes over a pulley and has a mass M hooked to it. So what that means is this force right here is mg, and that turns out to be the tension force. Okay. Now, this thing's actually vibrating, so it's technically not a node, right? But you'll notice if you actually do this experiment, which is one of the ones we do in our lab, but we didn't get to do it because we're not doing it in the lab this semester. But right next to it will be an antinode, and this, or excuse me, a node, and then there'll be a node here. So that's really what the length is. L is this distance from here to here. And I made a really big length, so we're actually going to have to deal with some pretty large mass here, or pretty large weights to be hung on here. So what I know is the velocity of a wave on a string is equal to the square root of the tension divided by mu. But the tension in this case is going to be mg, so I'm going to write mg over mu. And then I know that velocity is also equal to frequency times wavelength. But as we found before, we found that the wavelength in the previous example was in fact the same thing as this. It's 2L over N. So I'll just use that and say lambda is equal to 2L over N. We already know the frequency. So now I can say the square root of mg over mu is equal to F times 2L over N. I can square both sides. I'll get mg over mu is equal to 4L squared F squared over N squared. So M is ultimately going to be equal to 4 mu L squared F squared over N squared. So that's the general formula for the mass. So that's something really important. We've just, determined exactly for a given frequency, mass per unit length, and well, that's it, n number of nodes. That's exactly the mass that's going to hang there. So first I'm going to do the n equal 1 case. So n equals 1 implies m is going to be equal to 4 times 9.00 times 10 to the negative fourth kilograms per meter times L, which would be 3.00 meters squared times 120 Hertz squared over 1 squared, which means nothing. So when I actually do this, in this case, oh, also left off of G. Oh yeah, sorry. N squared G down here. Should probably write that in. Because remember, I did pull the mu up here. I knew I paused for a second because I felt like something had to go there, but that was because I forgot to divide by the G. So the G should definitely be there. And then this would be 9.80 meters per second every second. Okay. So now when I put this mathematics in, I end up getting a pretty large amount. I get 52.898 kilograms. So that's, on the order of 100 and some pounds. So that's a little bit higher than we'd really like to hang from a string necessarily, but that's the mass. And we've got part 1 answered. Now for n equal 2, you can see really the only difference is I'm going to divide it by 4. So n equals 2 implies m for 1 divided by, now I'll take the 2 and square it. So that's 4 in the bottom. So if I divide that 52.898, I get 13.224. Again, extra sig figs. That's equal to.
Where are you getting the 4 from?
Because the formula right here is n squared. So all these things are going to stay the same except for the n squared. Now the n became 2 instead of 1. So it'll be 2 squared, which is 4.
Oh, okay. I see. Never mind.
Okay. For n equals 5, then it's just going to be m of n minus, or n equal 1 divided by 25. Because 5 squared is 25. So in that case, I end up getting a 2.1159 kilograms. Equals the mass. So you can see in that case, obviously the larger the frequency, the smaller the necessary mass, or excuse me, the larger the number of modes, the smaller the frequency. The amount of mass, and that's because specifically the number of nodes is basically directly related to the wavelength in some sense. So you can think of it that way or whatever. Okay. Any questions on that? All right. We still got a few more minutes. So I use this stuff unwisely, by the way. When I took music lessons, I was trying to learn to play the violin. And I was horrible at it. My reasoning was the violin should be easier than the guitar because the guitar had 6 strings, and I can't say guitar without saying guitar instead of guitar. But anyway, so ignore my country accent. But I figured the guitar has 6 strings, the violin has 4, so that must be easier. Oh, could I never have been so wrong? It was horrible. But anyways, not only that, it doesn't have any frets, so you got to rely on your ear to make sure the music is right, as far as where you put your fingers and all that good stuff. So it was a real nightmare. So with that, I got another example. I'm going to call it example 4. And it says a banjo string is playing F is equal to 158.0 hertz. Instead of the desired 146.8. Hertz. What percent change of the tension will fix the problem? So I think you'll understand that question. In fact, what we're looking at here is I have my banjo, but I use this to tune it. And you can see right there at 146.8, that's my D3 string, which is the one right next to the drone string on the 5-string banjo. So it's the one right next to the short string. That's supposed to be playing at 146.87, I mean 0.8 hertz, but it's playing at 158.0 hertz. And standard G tuning or whatever. So that's why those particular notes were the ones that chosen. So what I want is this. What I know is the velocity of the wave is equal to the square root of the tension divided by the mass per unit length. And that, of course, is equal to the frequency times the wavelength. Now, remember, in the case of banjo string or any kind of stringed instrument, really the first harmonic's what you're shooting for. And we're talking about this not being changed by fretting. I don't want to shorten the length of the string or anything. I just want to adjust the tension so that the frequency is the right frequency. So we can even realize that the fundamental frequency implies that the L is equal to lambda over 2, or lambda is equal to twice L. So I can look at it that way. I can say the square root of the tension divided by mu is equal to the frequency desired times 2L. Well, that's not going to change from one case to the next. So I'm going to call this FA for actual, and the other one's going to be FD for desired. Okay, so this is going to be the same in both cases. The length from the nut to the bridge is the L, no matter what. So if I set 2L equal to 2L, what I get is 1 over F desired times the square root of the tension desired over mu. That mu is not going to change either, is equal to 1 over F actual times the square root of the tension actual over mu, which again is not going to change. So I can really get rid of that part. And in fact, I can make this a little simpler by squaring both sides. And I'll say that FA squared times FT desired is equal to FD squared times FT actual. So the desired frequency F desired, well, actually, let me say the desired tension. That's what I really want to solve for. So the desired tension FTD is going to equal the desired frequency over the actual frequency squared times the tension actual. Okay, but they're actually asking for a percent. So what they want is percent difference should equal, for starters, can anybody tell me why we're doing this? Can you tell me whether the tension needs to go up or down?
Tension needs to go down.
Needs to go down. So if we look at this, what we're saying is our frequency is too high, and that's on the numerator with FT. So yes, the tension has to go down. So we want the tension to decrease. And we normally indicate that by a negative percent difference. I've been calculating it as just a positive. I always take a positive, but this time I'm going to go ahead and do a negative. So I know that the new tension will be lower than the old tension. So the F desired tension minus the F actual tension over the F actual tension times 100 is really what we want. That's the formula we want to work out. So can we do that? Well, that takes a little bit of algebra. I've only got about a minute. So
I
what
think
I can
that's
do,
percent error, not percent difference.
yeah, it is. Yeah. In this case, it's one of those things. Yeah, you can actually call it percent error. It's the same thing. But when we're talking about the percent difference or percent change, maybe that'd be a better word. Let me call it percent change. But yeah, you're actually right. That is exactly the formula that we use for percent error. So it's kind of weird for me to call it that. I'm going to call it percent change because that's really what we're supposed to be using. But thanks for catching that on that. Now, if I want to calculate FTD minus FTA, I can just take this information I have, which is FD over FA squared times FTA minus FTA. That's what the difference is. So you can see that is actually FTA times FD over FA squared minus 1. Well, I can calculate that easy peasy. That turns out to be 1.1854, or it should be FTA times 1.1584 minus 1. So the top part of this percent change should be equal to the negative of 0.1584 times FTA over, now I need to put FTA down there, so that's just FTA. So it turns out this quantity should be negative 15.84%, meaning I had to decrease the tension by 15.84%, and that's the answer. Okay. Generally speaking, whenever you do a percent difference, you do the bottom is what you started with. Okay, that's the thing. Sometimes I actually accidentally will do it the other way, and it's kind of fair for me to do that because that's what they do at the bookstore. So they are allowed to have a percent difference of cost versus what they pay, given by this formula, but they consistently use the new price. So in doing so, they get a little bit more profit. So that's why I occasionally make that mistake, but this time I did not. So the percent change should be this. And the negative indicates I should decrease it. But that's really what you do to adjust your instrument. And in fact, when you're playing the instrument and you say play it versus something that's tuned like a tuning pipe or whatever, if you blow 146.8 and you play the 158, what you'll hear is a frequency, you'll hear two waves. One wave is the average of the two, and the other wave is what we call the beat frequency, which is the difference of the two. So when you play two strings that are supposed to, or two instruments that are supposed to be in the same note, and they're not, you'll hear a wall, 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 wall. Almost you'll feel like a vibration. And even though I suck at music, I can pick that up quite easily. That turns out, if you look in the next chapter, chapter 16, where they talk about sound, you'll see that you end up getting a wave function when two are combining like that, such that it's like sine of omega 1 minus omega 2, which is equivalent to frequency 1 minus frequency 2 times t. And then the other part is the sine of omega 1 plus omega 2 over 2 times t. And that's the other part that you hear. But when you go to tune them, you just adjust the tension until that wah, 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 wah goes away, because it'll get smaller and smaller as the tensions get closer and closer. Any questions on that? So this also helps you in a bad way if you're a musician, because what I would do when my instructor would tell me that's a little high pitch, I would say, okay, that means the frequency is too high. Okay, well, I can't change the frequency because that's dependent on the tension and the mass period length, but I can change the length. So I will, if the frequency is too high, I want to decrease it. And the only way I can do that is increase the wavelength. So I move my finger to a farther off distance from towards the nut and away from the bridge. But you can imagine that means there's like a 3-second gap between me playing the note and actually being needed to play the note. So this stuff really works. It's good, and it's good that you can think through it, but you don't want to do that from what I've learned as a student of music. So you guys, of course, are all free to go. If anybody has any questions, stick around. I know Tristan had a question about lab, so I'm here till the last person leaves.
Thank you.
Thank you. Have a good Thanksgiving.
Have a good Thanksgiving, Professor.
You too.
Professor, I just have a question on one on the lab.
Yes.
I have a question on number 6.
Okay. You want to share your screen with me?
That'd be fine.
Okay. Because I have no idea what number 6 is. What symbolic quantity m plus m a f does equation 1 suggest the slope is? Show me equation 1 real quick. I think it's what I know it to be, but there it is. Okay, so what you graphed was, it says the sum of the forces, but in reality it's just mg, right? You hung the little mass m, little m. So the tension is the only force acting on it, and that's going to be the left-hand side, so that'll be mg. You plotted mg, hopefully, on the vertical axis, not m. And if you did that, you also plotted A on the horizontal axis, and I suspect you found that the best power on A was 1. So here's what you do. Let me steal the screen back from you. So we had the summation of the forces is equal to m plus m times A. That became little mg is equal to m plus m times A. And if we compare, because we graphed this on the y-axis, equals m, we plotted this on the x-axis plus b. That's all you're doing. You see that the slope should be equal to m plus m, which is the 392.83 or something like that.
What'd you say though about before? About the A?
Okay, yeah, the A, you found the power of 1 probably to be the straightest line. Remember,
It was still kind of,
what's that?
it was kind of off still.
It wasn't a perfect straight line.
No, it was a great straight line, but it's just like it was pretty off.
Oh, okay. So the data wasn't that. It was more like you're talking about, like your straight line went like this, but the datas were.
Yeah.
Yeah, that's perfectly normal. That's exactly the way experimental science works. You find a
All right,
line
cool.
of best fit. It feels sort of linear, so you know it's good to go. So that's all you have to do whenever you're doing this graphical analysis stuff. You figure out, what do I plot on the y-axis? What do I plot on the x-axis? If you're ultimately going to tweak one of the values powers, whether it be this one's power or that one's power, you got to put that in the right slot. If it's on the horizontal axis, then you'll put, a to the 4th power or something like that corresponds to x. But in this case, it was a to the 1 power. So you compare these just by looking at what's what, and clearly y equals mx. There's b should be really close to 0. So the m plus m is the slope.
Okay.
Is that it?
So that answers the question though.
Yeah, it's just m plus m,
And that's
which is the 390, like
all right, cool.
392.83 or whatever it was.
All right, thank you.
No problem. Have a good one, Tristan. Have a nice Thanksgiving.
You too. And no class?
No classes until Monday.
What about the is there any online test upcoming?
Not that I know of. No, if you missed one,
Cool.
you might want to let me know and say, maybe take it, but I don't think you missed one.
No, I don't think I've missed any.
I think we had the 5th, the test 5 was due like on the 17th of last week.
Yeah, I did that.
Yeah. We got another one coming up that's supposed to be, that one was 10, 11, and 36, if I remember correctly. If we haven't done that yet, that'll come up, but it won't come up till after the break. But the other one I'm going to put up for this class is just going to be probably about elementary particles and waves.
Yep. I'm feeling good because I did pretty good on the midterm, and now I'm just cruising.
Good deal. Have a good one, Tristan.
You too.
Bye-bye.